In this session, we will discuss monochromatic fields. As we know, Maxwell equations are linear functions. This means that the Maxwell equations satisfy the following condition. For a linear function, for a vector function, if we have input, we have two frequency input, a omega 1 plus b omega 2. For a linear vector function, it can be expressed as a times f of omega 1 plus b times f of omega 2. This condition means that even though the input have two frequency, but you don't have to deal the combined frequency together. You can just deal with single one frequency. If you know how to deal with single one frequency omega 1 and omega 2, the total result of the combined input can be is the summation of each frequency. So we can just learn how to deal with single frequency problem. Okay? And for program with single frequency, or I should say that for fields with single frequency, we call it monochromatic fields. Actually, in our in previous studies, like such as EM fields or electric circuits, we have learned how to deal with single frequency problem. The useful tool we used is so-called phasor. Consider a function a, which can be expressed as a cosine function, with the amplitude absolute value of a, and the cosine function of omega t plus alpha. For such kind of function, we can re-express it as real part a times exponential j omega t. For such kind of function, if you can take exponential j omega t here and express it in the real part form, the a here is so-called phasor, which consists of the information of amplitude and phase. As we have learned the form of the phasor, usually we can represent a function as the phasor without using the real part here. Remember that this representation is only right for linear operator. What is linear operators such as plus, minus, or differential operation? For example, we consider the differential operation. We perform the derivative of a of t. According to the definition of a of t, we know that it will be d cosine omega t plus alpha here. And I believe you know the answer should be minus omega, absolute value of A, times sine omega t plus alpha. If you use phasor, the above can be expressed as by using phasor, the A function is replaced by this one. And as you doing differential operation, this one will become j omega A exponential j omega t. And clearly, if you perform the real part of the result, you will see that we will have the same result from this one. So the phasor operation can simplify our operation. But please note that the phasor form is not suitable for nonlinear operator, such as multiply. Consider two functions a of t. A of t is defined like this. And another function b of t is defined in this way. The phasor of each function is, for a of t, its corresponding phasor is capital A, which is in this form. And for b of t, the corresponding phasor is capital B, which is in this way. Okay? So let's see, without using function, what's the result of a of t times b of t? By taking the definition of a of t and b of t into here, we know that the multiply of these two functions is like this. Okay? But if you use phasor to do the operation, you will find that by using phasor, we take phasor here, you will multiply these two phasor and you will obtain the A B exponential j to omega t, and take AB into here, the result becomes absolute value of A times absolute value of B, and times exponential j to omega t plus alpha plus beta. And clearly, if you perform the real part, these two results are not the same. So this tells us a very important rule for the phasor. That is, real part of x times real part of y is not equal to real part of x times y. So the multiply operation is not a linear operator, so you cannot just use phasor to perform this operation. Next, we will try to find out the time averaging of the sinusoidal products. In previous slide, we have learned that the result for A of t times B of t is the following. To find out the time average result of this product, we have to integrate it over a time period. The period defined here is 2 pi over omega. So the time of averaging of this can be written as this. This means that you perform the time integral from 0 to t and divided it by the period, then you can find out the time averaging result. And we can take the result of the product into here. Okay, and clearly you can see that we have to perform the time integral of two items. For the first one, it is a cosine function with the angular frequency of 2 omega. And we can plot this function here. This is the time domain from 0 to t. The cosine function can be plotted as this one. And clearly you can see that the area in the positive region is equal to the area in the negative region. As a result, the integral of this item is 0. And for the second item, you can see it have no time dependence. So it can be regarded as a constant in the integral. So the result of the calculation will become like this. Okay, and this part can be rewritten as half real part absolute value of A times absolute value of B times exponential j alpha minus beta. And according to the phasor for A and B, this one can be written as half real part A phasor times the conjugate of B phasor. Okay, so if you want to perform the time average of the product of two functions, you can just use their phasor to obtain the result in this way.